Welcome back to our series on statistical methods. I'm Mark Ledbetter. This is lecture 25. We are in part B and we are discussing or continuing to discuss nested designs. And again, that's where one of the factors is actually nested within the other factor. So they are dependent upon, the second factor is dependent upon the first. All right, let's get started. Now let's talk about analysis of variance. So I can take the difference between an observation and the overall mean, sample mean, and I can add and subtract yi dot dot bar, and I can add and subtract yij dot bar, and now I can make these three, by grouping this cleverly, I have three terms, and you'll notice that the first term is the estimate of tau I hat, or it's tau I hat, it's the estimate of tau I, and the second term is the estimate of beta j nested within I, so beta ij hat, and the third term is the estimate of our epsilons, epsilon ijk hat, and this follows naturally. This next computation, this is the overall sample average, and so we're going to add up over I, j, and k. Excuse me, about to cough. We're going to add up all the values in the whole model, and we're going to divide by the total number of observations in the model, A times B times N. For our example, A was what? It was 3, B was 4, and N was 6. So 12 times 6 is 72. Yep. So we're just going to take every observation and average. Now, again, this is a balanced design. We're saying that K goes from 1 to N for all J's within all A's. And there is a way to adjust that like we've seen, but now it becomes a little more complex in that we have to add over, we would have not just NI's, so now it would be NJ, because it's nested within J. The K's are nested within J's. And then we'd have J equals 1 to BI. The number of, so for each level of I, we could have a different number of trees that we select. And then on the K's are the number of leaves within that tree. So we could vary all that if we wanted to, and it makes the formulas a lot more complicated. I'm just not going to go over those because, again, in the end, we're going to use a computer program, so I really don't see the necessity of just making such a mess in the notes, all right? But you can always Google these unbalanced designs and see all the adjustments to the equations. All right. But this is logical. Now the yi dot dot bar is, now we're summing over, we've got two dots. We've got a dot for the j and we've got a dot for the k, but we still have the I there. So we're going to sum over the j, sum over the k, and then we're going to divide by the number in each, which are on the top, right? So b and n. So we're dividing by b times n. So we're adding up all these observations within the j and the k for a certain I, and then we're dividing by how many we have. So again, if I remember correctly, we had 4, b is 4, and k equals 6, and a equals 3. All right, so we would be dividing by 24 here. And finally, we have the yij dot bar. So we're only summing for the k, all right? So we'll have 1 over n, and we add up within a fixed I, a fixed j, we add all the k, all the observations, and divide by n. So there'll be n observations in that nested portion. So for us, that would be the number of leaves within an individual tree. So we would add up the nitrogen content of those 6 leaves and divide by 6, n equals 6. Okay. The interesting thing about breaking up our difference here, the difference between an observation and the overall mean, and making it into these 3 terms, which are terms that both have a subtractions. So the only 2 terms that aren't canceled out over here are the terms on this side, which are the yijk and the y dot 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 bar. So everything else cancels out if we were just to add these. What's really nice about the way it's broken up is every time we take this decomposition and we square this, and so we'd square, so we square the left-hand side, we have to square the right-hand side. They're sums, and then we sum them up over I, j, and k. On this side, on the right-hand side, the cross products, the cross terms, this term times this term, the first one times the third, and the second one times the third, they all cancel out to 0. And so it's beautiful, but it's really messy, okay? So what we end up with is that we end up with the sum of squares of the first one plus the sum of the squares of the second one plus the sum of the squares of the third term. Now in this first term, we only have I. Oops, that's not very pretty. I is the only indice that's left. So we've already summed across j and k in both terms. And so we can say that there's b for the j's and n of the k's, because every time we add this, we sum this over k. There is no k in here, so they're all the same. So we'd have n of those. And for j's, the same thing, there's be b of those. So the only summation that's going to be left is this first one. So we end up with b times n times the sum of yi dot dot bar minus y dot 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 bar, quantity squared. This is going to be our sum of squares for factor A, and it's also known as between the treatments. Another word for between that's used a lot is among. So please don't get confused by among. That's not within, that's between. I like to use the word between so I don't mess it up by using vernacular English incorrectly, by the way. Among does mean between, but we don't always think of it that way, or at least I don't. And then the second term here, we don't have any k's. We have an I and we have a j here, and we have an I here. So we can't get rid of the summations for I or j, but we can get rid of the n of each over k. So there's going to be n of these that are identical for every ij combination. And so we see the n here, and then we see the summations and the sum of squares. And this turns out to be the sums of squares of b nested within a. This is also within each treatment. So SSB nested in a is within each ith treatment, okay? It's the sum of squares within the treatment. And then finally we have the residual or error term, and we have yijk, so we can't get rid of any of the summations up here. We have to keep them all. And so this term does not simplify. And this is our sum of squares of the error. It's also the sum of squares of the residual. You'll see in a lot of text as well. Okay, and I actually prefer the term residual, but our book doesn't use that, so I will try to conform in most cases to the book. Okay. or at least tell you when I'm deviating so you won't be confused. All right. So you'll notice that, I'll scroll back up here. You'll notice that we have a similar decomposition of the total sums of squares. That's this side, total sums of squares, as we did in the one-way ANOVA model. But now instead of 2 terms, we have 3 terms. Instead of just SSA and SSE, or SSTRT, I think we called it, and SSE, we now have SSA, SSB nested within A, and SSE. And I want to keep repeating this so hopefully it will sink into you. SSA is the sum of squares between the treatments, and for us that's the spray. SSB nested within A is the sum of squares within a treatment, within a spray, but between trees, our samples, which are trees. SSE, or SSR, is the sum of squares within a treatment, which is a spray, and within a sample, which is tree, but between or among the subsample, which in this case were the leaves, or leaves. Okay. So I'm using a different text to take some of the notes for this chapter, because I think this other text explains some of this way better than our text does. Our text does a great job in some areas, and in other areas it kind of falls down a little bit. So I really think that this is helpful. It was to me for this other book, for it to just spell out, hey, this is SSA. We could probably get this. This is between the treatments or among the sprays. But the second one, I might get this as well. This is a sum of squares within a treatment, inside a treatment, one treatment, which is spray, but between our samples, which in this case are the trees. Okay? And SSE is within a treatment and within a sample or tree, so with one spray, one tree, those are fixed. So within a spray and a tree that's been sprayed with that particular spray, it's the variation between the leaves of that one tree. So between leaves of one tree. Okay? All right. So I'm so used to lecturing in front of live people, I almost said, are there any questions? So, but you can't ask it right now. But if there are, please email me, or you do know that I'm happy to schedule a Google Meet with you as well. All right. Let's talk about the Anova table, but I want to point out that this Anova table, that these 2 columns are only for the mixed model. We're going to talk about a total fixed effects model and a totally random effects model. But right now we're dealing with the mixed effects model. The reason that it's chosen by both texts that I deal with as the example is because it's probably the most common. That doesn't mean that you won't run into the other 2. And we will, at the end of this, point out the differences. All right, so here's our Anova table. And so again, for all 3 models, these first 1, 2, 3, the first 4 columns, all 3 are good for all 3 models. Fixed, mixed, and random. Oops. Okay. So exactly the quantities we specified above in the decomposition, they're here, those 3 quantities. And the total is, of course, down here. And remember that this column adds up. SSA plus SSB nested within A plus SSE, those equal SST. That's our decomposition of the sums of squares. Okay. The same thing for the degrees of freedom. We have A minus 1. Okay. And then within a treatment, but among the samples, we have A times B minus 1. Okay, so there's B minus 1 within each tree, and then there's A treatments, so that's our degrees of freedom. And then within the error, or the residual, it's A times B times N minus 1. So within each tree, within each spray, we take N minus 1. Okay, and so there's A times B of those. And up here, within each spray, within each spray, we'll have B trees, so we take B minus 1, and then for each of those, and then times A sprays. All right. Our mean squares, as always, we take the sum of squares divided by the degrees of freedom for all three quantities. Now, here's where it's different. Right here. This changes depending on the model. So my F statistic, if I have a fixed and a mixed, is going to be, because this is nested within, I take the MSA and I divide it by MSB nested within A when it's random. Okay, and this one, I'll take MSB nested within A divided by MSE. I'm going to do that every time. So depending on, so this will be the same and this will be the same, but these two with asterisks, they're going to be different depending on the model. If it's fixed, I'm going to take MSA divided by MSE. We'll see that later. If it's all random, if A and B are random, then it's going to be the same as this. All right. So again, I'll point out the differences, but for right now, this is for a mixed model. These last two columns only work for the mixed model. Okay. All right. And with the degrees of freedom, we have A minus 1, A times B minus 1, AB N minus 1, and they add up to ABN minus 1. And that makes sense. We just want one, we want to subtract off 1 degree of freedom total. Okay? But we need to divide that up within the treatment, or between treatments, within treatments among samples, and then within treatments, within sample among observations. Okay? So we need those to add up to capital N minus 1. Remember, capital N is equal to A times B times N for a mixed model, or for a balanced model, I'm sorry, when a balanced model. All right. Otherwise, it becomes pretty messy for a unbalanced model. But it's still doable. It just takes some logical thought to get there. All right. But if I were in your shoes, just learning this material, I do understand that what I consider logical thought, that's based on a lot of experience working with this. So for you, it might be a lot more confusing. So I don't expect you to just be able to write out those formulas, one, either without thinking about them, or maybe even two, without seeing them first. All right? So some realistic expectations, I hope. All right, that's it for this video. If you have questions, please make sure you come to virtual office hours. If you need help prior to office hours, by all means email me. But when you email me, if it's about a problem, then email me what the problem is, because I may not have it available, and then your work on that problem so far. If it's code, then by all means send me a copy of the code, and in the email tell me where you're having the problem and that you need help. And I will get back to you as soon as it's possible. Please take care of yourself and stay safe, because we want to see you here next time.